Hey guys, welcome back to the Dynamics video series. This is the newest video for post exam 1 content, so everything from exam 2. That's what we're going to be starting today. I hope you guys did well on exam 1. I know you guys took it a little bit ago. So for exam 2, the main focus is going to be curvilinear motion, which basically means for exam 1, we were doing a bunch of linear stuff, boxes sliding, pulleys moving, free fall equations. The main emphasis for this exam is going to be things that are moving through curved, either like paths, so like the slot that you see on the screen, or some type of curved arc, things of that nature. So let's go ahead and get started with this problem, guys. So I think this was an old exam problem. The question is asking us to determine the magnitude of the acceleration of the 5 kilogram blue peg. Assume everything is smooth. The curve groove is vertical, so gravity is towards the bottom of the page. And we have a hint that the acute or the small angle between the straight slot and the tangent to the curvy groove has a magnitude of 57.5 degrees. And then be careful what you use for theta in this case. All right, so what's the first step for any of these problems always going to be? Do I need a free body diagram? Now, this is the first video for the polar problems, so the answer for every problem in this video is going to be no, but how do we figure that out before actually starting? So we have to figure out what we're being asked for. So we're being asked to determine the magnitude of the acceleration, right? So it's not a dead giveaway. It's not asking us for a force, so not a dead giveaway that we need a free body diagram. But we are looking for an acceleration, right? So we do have to count our degrees of freedom, right? So let's take a look at our picture. If you can imagine the straight slot spinning around on that pivot point, and then the little ball that's in the slot and in the curved line will be moving along with it, right, on that curved path, right? So imagine if we held this bar just in place, right? So this thing could no longer move. Would the ball still be able to move in the slot? Well, the answer is obviously no, right? Because it can't go up or down if it's locked to the slot and locked to the curved path. So we really only have 1 degree of freedom in this. So what does that tell us? That if we need to find one acceleration, if we're given one acceleration, we can do it without a free body diagram. And if you look at it, we're given an angular velocity and an angular acceleration, right? So we are given an acceleration in this case, so we actually do not need a free body diagram. So no free body diagram is needed for this problem. Okay, so I'm going to write down my given information, right? So we're given that r equals 0.2 over theta. And then we're given a bunch of values for theta, theta dot, and theta double dot. So remember, those dots, all they mean is the first time derivative and second time derivative of theta, right? So theta, we were given at 90 degrees. Theta dot equals 5 radians per second. And then theta double dot, so the angular acceleration, is going to be equal to 2 radians per second squared, right? So it's at this point that we have to remember that our our curvilinear equations, right? So this is a polar problem, so we have to actually pull them up. So they're going to be on your cover page for your exam, but I'm going to write them here on my problem just so that we can have it in the visual. So for the acceleration, right, of any polar, it's going to be equal to the r double dot minus the r theta dot squared, and that's for the radial component, and then plus 2r dot theta dot plus r times theta double dot, and that's for the transversal component. Okay, so if we want to find our acceleration, what variables are we missing, right? We have all the theta terms, so theta, theta dot, theta double dot are all present, right? So those are all already ready to go. Oh, and we do have r. So we have r here, but we are missing r dot and r double dot, right? So those two are what we need to look for. So at this point is when you can start doing derivatives like you guys started doing in class. We take the first derivative of r with respect to time to find r dot, and then we can do that again to find r double dot, right? And those will be in terms of stuff like theta. What I'm going to do in this video, and probably for all of these polar and path videos, for curvilinear motion is represent it in Mathematica, just because doing all the derivatives by hand would honestly take too long and cover this page too quickly. So I'm going to try and show you guys. I'm going to shift over to a Mathematica software, which you can use in your exam, and I'm going to solve it there, explaining it as I go. Alright guys, so this is the Mathematica tab where I'm going to be inputting the code I'm going to use to be solving these. Honestly, using Mathematica is a lot faster than doing it by hand, so I recommend, if you want to save plenty of time on your exam, definitely learn the program. I'm going to show you just a basic way of how I solve them generally, but you can also watch Dr. Everett's videos for more information. So firstly, we have to establish the theta as a function of time, right? How I do that in Mathematica is just writing out the word theta. And then let me make sure that everything's omitted. So I'm going to quit and then get rid of everything. That just deletes any temporary variables I already had in place. But we're going to make sure that theta is a function of time. Okay. All right. So it gave us this back. So now it knows that theta is a function of time. And then we're going to continue on. So we're going to establish what theta dot is, or what r is, right? So r, in terms of theta, based on our equation we were given in the problem, was 0.2 divided by theta, right? And theta is in the function of time that I just inputted above. And now, boom. So we have this expression for r theta. This is just what was given in the problem, right? And now what we can do, right, is we can take the r dot, right? So if we want to get r dot, remember r dot was just the derivative of r with respect to time, right? We can actually just do that here in Mathematica, right? So r dot, this is the variable I'm going to call it, equals, and then the derivative function of Mathematica is just a capital D, and then open close brackets. In this brackets, I'm going to put, what's it called, what I need. So I want the derivative of r with respect to t. So the first variable there, the letter r, is this function I have up here. And then t is what I'm taking the derivative with respect to. So this is dr dt, right? And that's what theta dot is. And then I'm going to check what this is. So this is the equation I would get. You could also do this by hand, where this theta apostrophe would be a theta dot term, and this would just be a normal theta term. But it's a lot faster done in Mathematica. And then you're going to see even faster when we do the r double dot, right? So r double dot is just the second derivative of r with respect to time. We can just take the derivative of r dot to get that. So we can do r dot with respect to time. And then when we solve for this, oh, let me get rid of this or fix this a little bit. Oh, what am I typing? There we go. This is our r double dot term, right? So if you notice, it took me probably about a minute while explaining it to just put in my r and then get my r dot and my r double dot, right? So a lot faster than doing it by hand. And then at this point, you could either write these down on your paper and then plug in the given theta double dot, and theta terms, or you can have Mathematica do the rest as well. So that's what I'm going to have it do. Okay? So I'm going to tell Mathematica that theta, and this is all just based on my given information in the problem, equals 90 degrees. Right? So 90 degrees, how I represent that. Theta dot, right? Not r, theta dot, which is given by that apostrophe, is going to be equal to, and then in my problem, theta dot was equal to 5 radians per second, so 5. And then theta double dot, with respect to time, right, is equal to 2 radians per second squared, based on my problem. So then I'm going to input that, make sure Mathematica saves this. This line means it read it, right? Semicolon, it means it didn't print anything, but that's fine. And now we can just call all of the terms that we just laid out. Enter. I want to let me enter. Okay, r double dot. And then let it work for a sec, and boom. These are all the values for r dot, and r double dot. We could solve it in about 2 minutes in Mathematica versus in 10 minutes by hand. So it's a lot easier. So I'm going to switch back over and then plug these values in that we just solved for. Okay guys, so I switched back over. So again, these were the values that I just solved for from Mathematica, right? So I didn't have to take any derivatives by hand. It can be all done with software in your exam. You're allowed to use that software in your exam. It's something I recommend. Just take some time to get used to it. Even just watching these videos could probably help you out. But if you really want to learn it, watch Dr. Everett's videos. But back to this problem. So I'm going to slide these over just for now. Let me lock this thing in place. Lock image. I'm going to slide these over just for now. Right. And basically, I'm going to have all the variables I already need to plug into this equation because I have all my theta terms, all my r terms, and I can basically solve for my magnitude of acceleration from here on. So let's just do it. The rest is algebra. So it's going to be r double dot, which we determined was 2.418, minus r, which was 0.127, times our theta dot term, which is given as, not 2, our theta dot was given as 5. And that value squared, and then that's our NR component, or our radial component, and then plus our transverse component, which is going to be 2r dot, and then r dot we solved to be negative 0.405 times theta dot, which was 5 again, and then minus, or not minus, plus r, which is 0.127 times theta double dot, which we solved, not solved, but was given as 2. And then close this off, and this was our transverse component, so our transverse direction. And then solving for all these, I can put it in a calculator, I already did. These came out to be, let me pull it up, negative 0.757 in the radial direction, and then minus 3.796 in the transverse direction. Now the question is asking for magnitude of acceleration, right? Not just these radial and transverse components. So how do we get the magnitude of this, right? It's basically just the Pythagorean theorem, or what we've been doing before to get a magnitude of a vector, where we take the square root of each of these components squared, right? So the negative 0.757 squared, and then plus the negative 3.796 squared. And then plug that in a calculator, we get that the magnitude of our acceleration is going to be equal to about 3.87 meters per second squared. And that's it, guys. It's going to be the end of this video. I hope it's made easy with the Mathematica. I think that's how I'm going to be doing most of these. We can maybe practice doing some of these derivatives by hand, but it's going to be a lot faster to use Mathematica and take up less room for me. So that's it. See you.